Minute and 20 seconds burn, just like that. Did you learn anything? Hi again. Welcome to Super Review number 2 for the AP exam. We are still broadcasting from Cummings' house while quarantine rock and rolls. So hopefully you have all of your slides for Super Review 2 down as we continue to look over past units of the school year. So let's get the Robo Rooster ready to rock. That's alliteration. All right, y'all, let's look back at acids and bases. When we started our acids and bases unit, the first lecture was a revisit where it was all pre-AP stuff, basically. So some basic things to know: your pH scale runs from 0 to 14. It's kind of a lie because we can definitely have pHs that are outside of that range, but that's just the generally accepted rule. AP doesn't usually ask about the ones that are outside of that 0 to 14 range, though. Under 7 is acidic. A pH above 7 is basic. Remember, there is a pOH scale that also runs at all times along with the pH scale. It's just the mirror image of it. While we start talking about things like Bronsted-Lowry, then it's important to know that acids are proton donators and bases are proton acceptors. We'll do an example of that in just a moment. Your basic way to find the pH of a strong sample is going to be the negative log of the hydronium content, or for a basic sample, the negative log of the hydroxide content. And remember the power of Kw. All right, Kw is going to be that constant for water, and you don't have to memorize it. It's on your AP sheet, but remember that it came in handy while we were studying the connections between all these numbers, because a lot of times, if you remember, we're looking at it'll give you a molarity and you got to get to the pH, or it'll give you the pH and you got to get to the molarity, or if you're doing something like Henderson-Hasselbalch, you'll have the molarity for concentration. It's gone. The concentration of the H plus, and it's an easy way to get to the concentration of the O minus without having to go through pH and pOH. If you know that Kw. So on your slide, it wants you to do the Bronsted-Lowry of H2PO4 minus. So we can take a look at that. If you remember, if you want to see the way that it acts, what I'm going to do is take that H2PO4 minus, we'll put him in water. All right. And what I look at here is I know that the H2PO4 minus is acidic. Therefore, it's going to behave Bronsted-Lowry the way that acids behave, and it's going to donate a proton. So in other words, one of the H pluses is expected to move from this compound to that compound during the interaction. So all I need to do, therefore, is write the result of that in my Bronsted-Lowry. And what we'll end up with is my buddy here with one less H. So now he's just going to be HPO4 minus 2, because we've also removed a positive charge. So now the negatives increased. And then that H was added to here. So now this is going to be H3O with a charge of plus. That's the hydronium ion. And you can see that, of course, the acid in water is going to do what you expect it to do. It's going to make hydronium flourish and therefore lower the pH. So there's the Bronsted-Lowry interaction. Now, keep in mind that there's conjugate pairs here that can be asked about. So remember, if I name him as my acid 1, then he's going to be able to produce his conjugate base 1. All right, so that's the connection between the two. So in order to connect your conjugates, it's always the leftovers after the change. So we labeled him as acid 1, therefore he would be base 1, the 2 1s just connecting them. All right. Therefore, water, who's amphoteric, remember water can act both basic and acidic. But in this case, if he's interacting with H2PO4 minus, he's going to be acting basic. So the H2O that's basic would be start off as my base 2, and this would be his conjugate acid 2. The 2's just connecting the ideas there. So one of the newer things that we did, though, was having to find the pH of a weak sample. And when finding the pH of a weak sample, it was nothing real difficult. It's just we had to utilize a rice table. Oh, I opened a water. All right, so taking a look, if you remember, if you identify, or rather, if you're given a sample of something and you using your strong versus weak rules, you can identify right away that the acid or base that you're dealing with is weak. Then you can't just take the negative log of its concentration. Instead, we have to add it to water in a rice table in order to figure out its pH or any other factor that it might be asking about. I say that because this question wants to know the magnitude of the equilibrium constant. So it wants to know it wants to know the equilibrium constant here after giving you a pH. So reading the problem that's in your slide, you'll see that's dealing with ammonia. So ammonia is by default a weak sample. So what I want to do is take that weak sample, NH3, and we'll be adding him to water. All right. Now we'll let this have the Bronsted-Lowry interaction where we know that my base here wants to be a proton acceptor. So on the other side, we will have one of the protons from water move over to the NH3. So when that happens, we're going to actually form ammonium. And once the water loses one of its H pluses, we'll have hydroxide over there. All right, so there's my basic setup. Now remember, we're dealing with the idea of a rice table here. So we want to build rice. I'm going to run out of space, I think. But anyway, so taking a look at what we know. So looking at the problem, it does give us an initial concentration of ammonia. It lets you know that we're starting at 0.1 molar. So what I can do right away then is say, all right, well, cool. So I've got 0.1 as my molarity there. All right, there's a couple extra sig figs that it gives you. If you remember, water is never a part of our equilibrium equation, so we can get rid of that guy right away. And then if you look at the way the problem's set up, initially there is no products being made. All right. So what we're going to want to do then is look at our change. Remember, it's going to be the coefficients that are going to help dictate our change. So since the zeros are over here, I don't have to worry about Q or figuring out a shift. I know for sure that it's going to shift towards the zeros. So this is going to be minus X, and this one will be plus X, and this one will be plus X. All right, now if you remember, the way that we get E is a combination of I and C. So over here, we're going to have 0.100 minus X, and then these are just ultimately going to be X and X, right? Now, in order to continue the problem, though, there's some other information that they gave us, all right, because I don't have any way to solve for X based off just looking at what I've written so far. But what the problem has done is it's given me a pH. Sorry, I'm looking for another whiteboard because I feel like I'm going to need this space. Dun, dun, dun. So let's see. Hopefully this will erase. Hey, y'all remember this from the last lecture? Yay. Yeah, it's erasing. So what's everybody been doing today? What'd y'all have for lunch? Was it tasty? Are your parents tired of having to cook so many meals for you? Or are they still packing a lunchbox the way that they did before this all started? Okay. So here's what I can do though. I'm given the pH, right, of 11.13. So I know if the pH equals 11.13, all right, I know that the pOH, all right, therefore must equal 2.87, right, because pH plus pOH is always 14. All right, so what I can ultimately do, or what I really want to figure out here, is if I can come up with this X, which is the OH minus concentration, I can plug and chug everywhere else. So what we want to end up doing then is saying, all right, well, if I know the pOH is 2.87, how do I turn that into the concentration of OH minus? Do you remember? All right, it's real simple. So we're just going to go 10 to the power of that pOH, I'm sorry, that negative pOH, so it's going to be negative 2.87, all right? And when you do that, you're going to get an OH concentration of 0.0013. All right, so if you run this, I'm gonna write it over here on this board. All right, my OA, the X here ends up equaling 0.0013. All right, so now I know the value of X. So if that's the value of X there, that must also be the value of X here. All right, and then over here, it's going to be 0.1 minus X. All right, so it's going to be 0.1 minus 0.0013. And we're able to find all of these amounts. Now, but when you do this math, you'll get 0.0987. All right, and that's going to be my my equilibrium here of the NH3. So now I've got all three of these values, and we just need to remember. All right, well, if we're looking for K, all right, remember it wants the equilibrium constant. If we're looking for K, how do you find K? And remember, it was the product of the products over the multiplication of. Sorry, my phone's going off. Of the reactants. So ultimately what we need to do here, I wrote it like that, is we'll take these two multiplied by each other. All right, so we'll go K is going to equal, and remember, you could do an unsubstituted equation here, which is always a good idea. I'm just out of space because this is my window classroom. But you could show, it's always a good idea to show that K is going to equal the NH4 raised to, concentration of NH4 times the concentration of OH raised to no powers because there are no exponent, there are no coefficients, right? Because we'll raise it to the power of coefficients. But anyway, so it's going to be 0.0013, all right, times 0.0013, and we're going to put that over my 0.0987. All right, because my reactant is the denominator. And when it's all said and done, and you type this into your calculator, you will finally find the value of K, which in this case is going to be 1.7 E5. Hello. Might have said E5 a second ago, -5. Sorry if I did that. Yeah, maybe. Another thing that we looked at was looking at the pH of salts and the general process to figure that out. If you remember, the trick was knowing your rules of what's strong and what's weak, and then being able to figure out the parents of your salt. Of course, your salt is going to be any ionic compound, all right? So what we can do is pick an ionic compound and just analyze his parents. So let's do ammonium nitrate. So ammonium nitrate is NH4NO3. All right, it's two polyatomic ions bonded to each other, all right, to create salt. I want to know is, will this salt make a solution more acidic or more basic? All right, well, in order to do that, I need to look at who his parents are. Who's your mommy and who's your daddy? All right. So ammonium's daddy is going to be NH4OH. His daddy left when he was very young, so don't bring it up. Nitrate's daddy is going to be HNO3. So you'll notice all I did was I took the cation and I threw hydroxide after it. I took the anion, I threw hydrogen before it. And now we can analyze the strength of the parents to figure out the basic range of pH that each one can produce by looking at strength. So if I think about my hydroxide rules, I say, okay, well, I know that hydroxides are strong if they're bonded to a group 1 metal or strontium, calcium, barium. In this case, it's not. So this is a weak sample here. All right. I know that acids are strong if it's I bring clay, or if there's at least 2 more oxygens than hydrogens. Hey, look, there are 2 more oxygens than nitrogens because nitric acid is strong. So the strong wins. So what would you guess the pH, the resulting pH of this salt is? I would guess that it's less than 7. Less than 7 because the stronger parent is the acid, and acids have a pH less than 7. For those of y'all worried about my cough, I've never had a fever, and it doesn't hurt to cough, and my throat's not sore, and I haven't died. So, hooray. Okay, so let's change gears a little bit to solution equilibrium. So this was our last unit of the first semester. And we started off with buffers. This was the disturbance of already existing solutions is what we were looking at, which had to do with things like titrations and stuff. But remember that the definition of a buffer is real important. A buffer is created by a weak acid and its conjugate base, or vice versa. So it's really important that when you're looking at a buffered system, that those two things are present for it to actually be buffered. If you remember, the point of the buffered system is that it's set up in a way that it can resist change. Since it's got both the weak sample and its conjugate, if you add a sample that can disrupt the pH or pOH of the buffer, it's got the ability to have one of the pieces of the buffer produce the other. It will take that invader, all right, it'll split them up, and if it's, depending on which side is added, a cation or an anion, it'll interact with the buffer to produce stuff that's already in there to help maintain the equilibrium that it already had established. The way that the equation that we use when dealing with buffers was Henderson-Hasselbalch, and you can see that that is sitting on your slide. So let's do a problem. All right, it says calculate the pH of a solution in which 0.53 molar of H4NO2 and 0.5 molar sodium H6H4NO2. That's what it's containing. So what I can see right away by looking at the problem is that the first solution, or rather the first compound mentioned, is a weak acid. I know it's a weak acid because it starts with H and it contains carbon. Weak. then I can find its conjugate base in the other compound. But remember, the conjugate in these buffers is almost always hiding in the form of salt, which is why that sodium is there. The sodium doesn't matter because when it goes into solution and dissociates, then it's just going to be the buffered system of the weak and the conjugate that matter. But just because of the way the compound has to be built in order for you to handle it, the conjugate is going to be hiding in a salt. So there's a piece of missing information here. If you remember when we took this test, all of these problems, unless you were solving for it, would give you the Ka or the Kb. So in this case, I have to tell you right away that the Ka of this acid, this is just the standard number that will be given to you. In this case, it's 1.4 E negative 5. All right. And that'll be important. So what we need to do then to use Henderson-Hasselbalch is we will, whoa, little markers all over the place. Just follow along with the equation and you'll see that we're looking for the pH. So we can just go right away and say, all right, well, pH equals, all right. And the equation says pKa, right? Okay, well, remember what the P stands for. The P actually stands for negative log. That's the same thing for in pH, negative log of the hydronium. So I'm going to right away go negative log for the P, and then this number for the Ka. Still following the equation, it then says we're going to add that to the log of the ion over the actual acid sample. We're going to add that to the log, and here's where some of y'all get confused, is what to put over what here, all right? And it's always the ion that goes on top or the item that's hiding in the salt, because it will be an ion when it does its buffering job, because once it's dropped in solution and dissociates, that in this case sodium won't matter anymore. It'll be just the C6H4NO2 minus that is floating around. So if you look at the way the numbers are assigned, I'm going to put 0.5 over 0.53 maybe. And now I have filled in my equation. We're able to solve for pH, and I'm going to get a pH of 4.83. Come here. Stop barking. Oh, you little girl. All right, here's a more fun problem. Now, I'm not going to go over a full titration, but if you remember, a titration was simply a bunch of invader problems over and over again, where we were constantly adding an acid or a base to an already established solution and basically seeing who won. All right, it was like a war, and sometimes the titrant would win, sometimes the analyte would win, and we would find that using kind of a using a limiting reactant type idea, where we need to find the moles of our starting substance, the moles of the item that is invading, and whoever is present in the lower amount of moles is the one that's going to lose the battle. And that's what we'll remember as we work out this next problem. All right, so let's do an invader problem. It looks like we're going to have HCl being added to a buffer system, including acetic acid and sodium acetate. So what we have to ask ourselves is, when we're adding HCl to it, what's it going to interact with? All right, it's not going to interact with both parts of the buffer. The whole point is that one part of the buffer can handle a type of invader and produce the other. The other thing in the buffer can handle a different type of invader to produce the other guy. So we need to take a look at what's being added. So what I'm going to do is I'm going to say, all right, well, HCl is the invader, all right, but I don't care about the Cl, all right. It's really, and this is what we always did, it's just the H plus that's going to be doing the invading, all right. And we're going to see how that's going to end up throwing off pH and and stuff. So if I look at the sodium acetate and acetic acid, then I need to figure out, well, which of those guys does H plus want to interact with? And it's not going to be the acid, all right? No. It's going to be the ion that is hiding there in the sodium acetate. So remember, when the sodium acetate dissociates, it's just acetate that's floating around. So it's going to interact with the C2H3O2 minus. All right. If you remember in class, I would shorten acetate with AC, so I'm going to do that from here on. I mean, you're cool to do that, but that's what it's going to produce is acetic acid. All right. So what we've done in that first step is we've proven the buffer, right? By him being added, all right, what was the end product of his interaction in the buffered system? Hey, look, it produced acetic acid, which is the other dude that's already in the buffered system anyway. So it's going to try to maintain our current pH. Now, what I do need to do is figure out, well, who's going to win the battle based on the molarities and amounts of everything being added. So I need mole counts. In order to get moles, if you remember, molarity is moles over liters. So if I want moles, it's molarity times liters. So you need to watch your units real careful because milliliters is what's given. So it's going to be a triple slide to the left in order to turn milliliters into liters. So with all those things floating around in our head, I'm going to look at this, look at the problem, look at the numbers in the problem, and I first want to say, well, how many moles of the H plus are there? All right. Well, in order to get the moles of H plus, I need to take the molarity of the H plus. So if you look, it's 0.525. Do you see? 0.525 molar times the liters of it. How much was added? 125 mils, which is the same as 0.125. So if I multiply those two numbers, again, 0.525 times 0.125, I get 0.0656. I get, should I change colors? I get 0.0656. And that's my mole count of the H plus. All right. So what about the C2H3O2? All right. Well, again, if we look at the problem, the molarity of both parts of the buffer is 1 molar. All right. They're both 1 molar. So I'm looking for moles again, molarity times liters. So it's going to be 1 for the molar. And then how much of him is there? All right. And it looks like same amount, 0.125. So, or sorry, 125 mils, 0.125 liters. So 1 times 0.125 is, of course, 0.125. All right. Now, it's important for, now we're going to analyze these two numbers right here, all right? And because they're going to battle against each other and one of them is going to run out. But keep in mind that there was an initial amount of acetic acid. So this is not just a 0. I can figure out the moles of him as well because there's going to be a whole connection here for everything. Now, if you look at the HAC and you look back at the problem, you'll notice that, again, it's the exact same deal. It's 1 molar at 0.125 liters. So when you multiply those together, you're again going to get 0.125. There's my mole counts of everything. Limiting reactant. The smaller number will be used up first. So what I'm going to do is figure out, well, which one of these is the smaller number. It's very obviously 0.0656, which means the invader is going to lose. So I'm going to say, all right, well then minus 0.0656 minus 0.0656. And then what happens on the other side? Not a minus, all right, we're producing that. So plus 0.0656. And we can get some numbers here, all right? So switch colors again. If we do this, it's obviously 0, all right? If I subtract these two values, I get 0.0594. All right, and then over here, I'm going to get 0.191. All right, here's where there's a million hands in the air because we've done a lot of work so far, but I can't see you. All right, so cool. Now keep in mind what we figured out here. These are mole counts, right? And what we can do is we can, in order to answer the question, all right, it wants the pH, we're going to use Henderson-Hasselbalch because we knew from the very beginning we were dealing with a buffered system. However, Henderson-Hasselbalch is based off of concentrations. All right, not mole count. So if you remember, there was a hidden step here where I wanted to turn these moles back into molarity. To find molarity, it's moles over liters. What's the total liters now? Well, we had 125 mils. We dumped in 125 mils. Guess what, baby? We had 250 mils now. Boom, drop the mic. I need another marker. So 250 mils is going to be 0.25. Oh, so we're going to divide both of these by 0.250. Divide it by 0.250. And this is going to give me some new mole counts. All right. So now I've got a mole count here. Well, you know what? Let's, because I'm about to be out of space, let's plug into Henderson-Hasselbalch and I will solve those two little mini problems, ouch, as we go. So Henderson-Hasselbalch states that pH equals the negative log of Ka. Did they give you Ka in the problem? No. So just keep in mind, if you're not solving for Ka, it's a given value. So our Ka here is 1.8 e negative 5. That's a given number, 1.8 e negative 5. Plus the log of the ion over the actual sample. All right, so here's where we have to make sure that we keep it straight. All right, hey, look, that's the ion. There he is, the ion. So this here, the 0.0594 divided by 0.25, if you type it in, it's 0.238. So I'm going to go 0.238, all right, over the concentration of the actual sample, all right, which is going to be 0.191 divided by 0.250. In this case, I get 0.764. We've got Henderson-Hasselbalch ready to go, and now it's a plug and chug. I get a pH of 4.238. Remember when we lived down in the ag arena? We had one lecture down in the ag arena. Well, that one lecture was over solubility product. Solubility product was the moment where we looked at the lie that an insoluble solid doesn't dissolve at all. And that's a lie, and since we don't want to do complete lies in chemistry, remember there was a little bit of solubility in anything, and that's what KSP looked at. So let's do another fun problem. All right, what do we got here? Looking at this solubility, it says find the KSP. All right, so we're wanting to find the K of this insoluble substance. And then it gives us our situation. So what I see is the silver chromate. All right, now silver chromate, following your solubility rules, you know is predicted to be solid. But if you're asking, if it's looking for the KSP of one of these items, the very first thing that you were to do was split it in a rice table, was to take it and say, all right, well, if it's going to dissociate, here's what it looks like in a rice table. So I'm going to take my Ag2 CrO4, all right, and again, this dude's solid, right? and we're going to split him into his parts over here, which is going to be the Ag plus and CrO4 minus 2. All right. All right. Now keep in mind that we do have to be balanced, so that 2 right there is a big deal. And now we are looking good. So it's a rice table that we're setting up. So let's make him look pretty. All right. Now, solids can never go into rice tables. So what was really nice about these KSP problems is that this guy right here had no bearing on anything. All we needed to do was analyze these two items here at the end, the two products. So what I know starting off the bat is that in the reaction there started off being none of these, right? So we can assume that we're starting with zeros with the way that the problem is written. All right. And then we can represent our change. Remember, the C row is going to take the coefficients into account. All right, so this is going to be my plus 2x, and this will be plus x based off of those coefficients. All right, by joining these together, all right, remember I plus C equals Z. So this is just going to be 2x and x. All right, nothing that we're having to think too hard about. And then if you read the problem, you'll see that you are given the concentration of the CrO4 minus 2, the CrO4 minus 2. And you're given a concentration of 6.5 E negative 5. All right, so basically it's telling you that X is 6.5 E negative 5. All right, is this concentration. All right, I think I missed a sig fig there. Does it give us an extra one? Yeah, there's a 0 here. So, sorry. All right. Okay, well, if I know that that's x and this is 2x, well, then that number twice is going to be the other missing value, and I get 1.3 e negative 4 here. 1.3 e negative 4. All right, and now we can move forward to find the KSP. Now, keep in mind that in order to find K, it'll be the products over the reactants, but in this case, there's no value for the reactants. So really, it's just going to be those products multiplied together. So if you wanted to write an unsubstituted equation, it would just be KSP equals, all right, and that would be the concentration of silver ions to the power of 2, right? Because we always raise it to the power of the coefficient, times the concentration of CrO4 minus 2, which is using these numbers here. So it's going to end up looking like KSP equals, all right, there's not going to be a denominator, so we'll just use our numerator of 1.3 E negative 4 squared, all right, from that 2 up there, and that'll be times 6.5 E negative 5, no exponent there. And then KSP, all right, is going to equal 1.10 E negative 12. I'm sorry, there's, you know your sig figs are good, right? 1.10 E negative 12. That's your answer there in green. The last main topic we want to cover in today's lecture is going to be the start of second semester, which was thermochemistry. All right, that was fun, studying energy. So some basic stuff there. Definitely to look back in your notes. Keep in mind, I just want to remind you that this is an overview. All right, everything I taught you throughout the year is fair game. So make sure you go back and like exo versus endothermic, know those basics. I know this year there's no multiple choice, but and that's where a lot of the, a lot of my lectures have those moments where I like, and they're definitely going to ask you this question in some way. All right, well, with multiple choice gone, man, there's just no telling. None of us across the country really know what to expect on this year's FRQ only exam. But anyway, exothermic versus endothermic. That slide goes over basic things like when it's negative, when heat is going in or heat is going out. That's the foundation of all thermo. So make sure that you do know that. Now, there is a calorimetry problem on there. There's a high probability that they'll ask you to do a calorimetry problem. So if you remember, it's Q equals MCAT, right? Don't have to memorize that. So let's make sure we remember what these variables are. I don't know if y'all can see, but it's a beautiful day out there. Those are gonna come through. Yeah, it's okay. Well, that's the sky. But I would my daughters are in the front yard right now washing my truck because they want to be, not because they're just dying to be outside. So wouldn't it be awesome if we finish and I get to go hang out with them? Okay. What do I do? Stay. Let's take a look at this calorimetry problem. I'm going to get the equation up here, which of course is Q equals MCAT. All right. Q being the amount of energy, M the mass, C the specific heat, and then we have our change in temperature. So if you look through this problem that it gives you, it starts rattling them off. It says calculate the final temperature. So remember, in regards to temperature changes or any triangles at all, it's always the final minus the initial. So you're definitely going to want to have that in mind anytime you're dealing with these types of equations. But it gives you 1575 joules of heat are removed. And that's where they like to see if you're a smart student. Are removed. Exothermic, if it's removed. Negative, if it's exothermic. That 1575 is not a positive number. It's negative 1575. I hate it. So watch out, because that's the way that they layer those concepts to see if you know that. But that's your Q. All right, if I look through the problem, it does give me a mass of 85 grams. All right, grams is good. Those are the units that you want. So we've got 85.0. All right. Is it 0.0? It is. Okay, C is the specific heat. If we look in the problem, we've got a specific heat given to us of 2.4. All right, and then all we need is our change of temperature. Now remember, it specifically already asked us for the final temperature, which of the two in this last little variable is the first one. So what I'm missing then is the final temperature minus, and what does it give me for initial? It says the initial temperature is 23.5 degrees Celsius. All right. Now remember, degrees Celsius was okay here. Some of y'all are always real nervous to keep degrees Celsius in an equation because gas laws teaches you to never do it. But this is going to be an absolute difference of numbers. So even if you go to Kelvin, you'll get the same answer. So for thermochemistry, or rather for calorimetry, I should say, you don't have to convert to Kelvin. So what is the final answer? Well, plug and chug, that's simple algebra. I get 15.8 degrees Celsius. Jarvie, leave the camera on. Jarvie, come. Did I say hi to the people again? Who's your good girl? Come on. No? Come here. Come up. Come on, you gotta want it. Oh, you got kisses? You got say hi, everybody. No, look at them. They want to see your pretty eyes. Oh, that's a pretty dog. That's a pretty dog. Okay. What about Hess's law? All right. If you remember, Hess's law was going to be a way for us to calculate heat of reaction. This is when we were looking at things like enthalpy. Remember, there was several ways for us to find enthalpy, and this way. Remember, don't forget Big Mama. Remember Big Mama? She's important. But anyway, again, look through all of your notes. This is just as much review as I can fit into a lecture. But using Hess's law is where we are giving the standard enthalpy reactions for several reactions, and then there's a goal reaction that we're trying to match. Using the values associated with all the given reactions, we can move them around, which will alter the enthalpy values that are given in order to equal our goal. Now, this problem that we're doing here doesn't give us the goal. It actually double dips into being able to write your goal, which it wants the heat of combustion for ethane. So we're going to have to do that first. Now, remember, when you're looking for this, the trick was that you can only have 1 mole, right? You can't change the 1 mole of the substance that you're dealing with. Papers are about to fall. And in this case, we're dealing with ethane. So my ethane is C2H6, so it's combustion, right? So we're going to go C2H6, and we want it to combust. The goal was, or not the goal, the rule was that has to stay a 1, all right? So during combustion, we know that we're going to have our hydrocarbon here reacting with oxygen to produce carbon dioxide and water. All right? And now we want to work on balancing the equation. So the carbons are easy. 2 carbons, now there's 2 carbons. 6 hydrogens, now there's 6 hydrogens. But my grand total of oxygens on the right-hand side right now is 3 plus 4 is 7, but I'm not allowed to alter ethane. Therefore, we're going to have to use a fractional coefficient, which was real simple. If you remember that, I mean, the trick was whatever that number is, just put it over 2. So there's my balanced equation. Now, I don't have these pre-written for you. I'm going to show you the slide again in case you're behind. You can pause it. And what you'll want to do for sure is have those standard enthalpies of reaction data in front of you so that you can keep track of what I'm saying. Because what I want to do is I want to do whatever's necessary to match each of those to this goal reaction. So for example, when I look at the first one, I can see that the ethane is on the wrong side. Do you see how in that first one, C2H6 is a product? I don't want it to be a product. I want it to be a reactant, like it is in my goal reaction. So what do we do to the given enthalpy value if it's on the wrong side? Flip the sign, baby. Just flip that stinking sign. So instead of using the negative 84.68, I'm going to use a positive 84.68. All right. Moving to the second equation that's listed, what I notice is that the carbon dioxide is there and it's in the correct place. However, the coefficient's wrong. It's a coefficient of 1 in the given equation. I need it to be a coefficient of 2. How do you fix it? Multiply the number by 2. The given number on your slide is negative 394. Negative 394 times 2 is negative 788. All right. Finally, there's one more reaction given, and it's got the water in it. All right, it's got the water that I need, and it turns out that that water is again on the correct side. There's just the wrong number of them. The reaction that's given has there being 1 water, I need 3 waters. So to make the number correct, I'm going to multiply the given value by 3. The given value is negative 286 kilojoules times 3 is negative 858. If I sum all of these together, now keep in mind that you can check your work by doing all of these actions to the reactions and rewriting them as such, and then canceling out items that matches reactants and products. And if you've done it right, it'll match this perfectly. But if I take the sum of these values in this case, you will get the heat of reaction for the combustion of 1 mole of ethane to be negative 1561. Negative 1561 kilojoules is your answer. So some facts here to remember to have in your mind is that when you're dealing with entropy, which is S instead of H, that you're dealing with disorder. And it's the movement of signs here are a real common thing that they like to know. So remember, spontaneous reactions, another way to say spontaneous is if it's thermodynamically favored. All right, that was your synonym. But spontaneous reactions will have a negative change in G, your Gibbs free energy. But anytime that the entropy is increasing, there has to be an increase of S. One of the ways that definitely happens is when particles become more random. And when you're thinking about states of matter, the most random state of matter is the gaseous state. Therefore, if a reaction is producing more moles of gas, that's going to be increasing S, all right, because the entropy wants that madness, that wildness. Another equation that I don't have a practice problem for right now is Ghetto-Homies. If you remember, Ghetto-Homies was real easy to plug and chug into in order to find your Gibbs free energy, but the S and H are never given in the same units. One of them is in kilojoules and one of them is in joules, just because that's the commonality of their readings. Convert one to the other. Don't mess that up. It's a very common mistake when using Ghetto-Homies. One more time, I want to remind you that this lecture is supposed to be paired with the notes from these units, and the Schoology practice will be hitting the in-between topics that I might have glazed over, passed over, went over, didn't go over during these last 55-ish minutes. Peace.